The object designated 3I Atlas is currently making an extremely close approach to the Sun. This third confirmed entity, originating from beyond our solar system, is hurtling through the inner planetary region, crossing within the orbital path of Mars and accelerating towards its closest solar proximity at a speed approaching 68 kilometers per second. However, precisely as Earth's terrestrial observatories will be rendered inoperable due to a solar conjunction occurring in mid-October, Atlas will plunge into the Sun's intense energetic field, concealed from terrestrial observation. This will leave every scientific investigator with naught but conjecture and mounting queries regarding its peculiar chemical composition, immense dimensions, and unpredictable conduct. What outcome can be anticipated when an object estimated to be 50 kilometers in diameter, originating from another star system, encounters the solar wind at full velocity, completely hidden from human sight? The schedule, the potential hazards, and the unresolved enigmas all commence at this very moment. At present, this celestial wanderer is charting its distinct course within the orbital confines of Mars, inclined approximately 5 degrees from the ecliptic plane. This trajectory is so steep and retrograde that it effectively intersects the solar system's plane almost head-on. Its orbital inclination stands at 175 degrees, a figure that starkly emphasizes the profoundly alien nature of its origins. The vast majority of comets and asteroids traverse the solar system in a broadly similar direction to the planets, but this object is a genuine outlier, approaching from the diametrically opposed direction and crossing the planetary thoroughfare at a sharp angle. The figures alone narrate a tale of relentless acceleration. When initially detected by the Atlas survey in early July, its velocity was already an impressive 58 kilometers per second. Now, as it plunges ever deeper towards the Sun, that speed is steadily escalating, on course to reach nearly 68 kilometers per second at its perihelion. Attempt to visualize this scenario. A fragment of interstellar detritus, potentially as broad as a moderately sized city, hurtling through our solar system at a velocity exceeding that of any spacecraft ever constructed. At these speeds, it covers the distance between Earth and the Moon in a little over 1 hour. Perihelion is slated to occur on October 29th at 11:55 UTC. The closest passage to the Sun will take place at an estimated distance of approximately 1.36 to 1.40 astronomical units, situated just inside the orbit of Mars, yet still comfortably beyond Earth's own orbital path. Unlike those solar grazers that flirt with catastrophic destruction, this visitor will not descend into the Sun's corona. Instead, it will skirt the periphery of the inner solar system, navigating a course through the region where the solar wind and electromagnetic fields attain their peak turbulence. The geometric alignment places it within the constellation Virgo at its closest approach. However, from Earth's vantage point, the Sun's overwhelming brilliance will render it entirely invisible. The orbital parameters catalogued by the Minor Planet Center corroborate a hyperbolic trajectory, signifying an eccentricity greater than 1. This is a mathematical signature that guarantees its permanent departure from our solar system. Its inbound trajectory, outbound escape, and the sharpness of its solar swing all indicate a brief, singular passage. Every kilometer it traverses now brings it closer to the Sun's dominion and further from the only observational positions capable of tracking its journey. This is the geometry of a cosmic interloper, positioned within the orbit of Mars, deviating by 5 degrees from the ecliptic, accelerating from 58 to nearly 68 kilometers per second, with a rendezvous with the Sun scheduled for October 29th. The numerical data are precise, the timetable is fixed, and the opportunity for direct observation is diminishing with each passing hour. From Earth's perspective, the calendar presents a stark reality. October 21st, 2025, marks the superior conjunction. This is the moment when 3I Atlas will slip directly behind the Sun, concealed from every ground-based telescope and even most space-based observatories. For the subsequent several weeks, the Sun's effulgence will dominate the sky, obscuring any trace of this interstellar visitor. Astronomers refer to this as a blackout, an enforced period of silence during which no new data can be collected, regardless of the sophistication of the equipment. The Sun's disk acts as a blinding curtain, blocking not only visible light but also the majority of infrared and ultraviolet signals. Imagine the profound frustration. Following months of urgent collaborative efforts, over 120 observation campaigns, emergency override protocols enacted at flagship telescopes, frantic exchanges on communication platforms, and late-night video conferences, the entire global initiative is compelled to a halt. The celestial geometry is unforgiving. Solar elongation, the angular separation between the comet and the Sun, as observed from Earth, dwindles to virtually zero. Even the most ambitious adaptive optics systems or twilight observation techniques prove ineffective. Detectors face the risk of damage, and safety protocols trigger automatic shutdowns. The final dependable data points are gradually received around October 18th, as the object's apparent separation from the Sun dips below critical thresholds. Coronagraphs, those specialized solar observatories engineered to block the Sun's blinding central disk, offer minimal assistance. At magnitude 12, 3I Atlas is simply too faint and too compact to be discernible against the turbulent luminosity of the corona. Deep background subtraction and image stacking techniques, highly effective for brighter solar events, prove insufficient in this instance. No confirmed detections have emerged from the SOHO, Stereo, Parker Solar Probe, or Solar Orbiter missions during this critical window. Attention briefly shifts towards Mars. In early October, orbiting satellites such as Mars Express and the ExoMars Trace Gas Orbiter managed to capture a limited number of long-exposure images and low-resolution spectra as the comet skimmed past the red planet. Their vantage point afforded a fleeting advantage, a final glimpse before the Sun's intervention. However, even these datasets are constrained. The coma appears as a faint, fuzzy point of light. The nucleus remains unresolved, and the tail is imperceptible to their sensors. Attempts to redirect Mars orbiters for perihelion phase imaging ignite debate within mission teams. Resource limitations, orbital geometry, and instrument safety considerations ultimately prevail. The opportunity is lost. So, when will the silence be broken? The window for reacquisition opens in mid to late November as 3I Atlas emerges from behind the Sun and reclaims a position in the pre-dawn sky. By then, it will be receding both in distance and brightness, yet still within the observational reach of powerful telescopes and dedicated amateur astronomers. The calendar's next significant marker is December 19th, 2025, when the comet achieves its closest approach to Earth, at approximately 1.80 astronomical units just prior to the winter solstice. Between the period of conjunction and its reacquisition, the narrative is one of anticipation and uncertainty. Every hour lost to the Sun's glare represents an hour during which the most anomalous interstellar object ever recorded could undergo transformation, fragmentation, or simply fade away, unobserved. The scientific clock is ticking, and the world awaits the first signal to pierce the solar curtain. The size, in this context, refuses to settle into a single definitive measurement. Early photometric readings, derived from dozens of telescopes across both hemispheres, suggest a nucleus ranging in diameter from 5 to 50 kilometers. This potentially marks it as the largest interstellar object ever observed. This range is not a mere rounding discrepancy. It is a symptom of an object obscured by its own activity. The coma, a diffuse envelope of gas and dust, expands so densely around the core that even the most potent ground-based mirrors and Mars-orbiting cameras are incapable of resolving the true solid body. Instead, astronomers are compelled to infer mass and volume from indirect indicators: how the object brightens, how its light scatters, and the rate at which the coma thickens as it approaches the sun. The color, too, tells a story of constant flux. Throughout June and July, the coma's spectrum exhibited a reddish hue, possibly indicating the presence of complex organic grains or larger, slow sublimating particles. By August, a transformation occurred. The coma shifted to a distinct green, a color rarely observed with such intensity in comets within our solar system. Spectroscopic campaigns, including those utilizing the Canada-France-Hawaii telescope and the JCMT, meticulously tracked this evolution in real time. The apparent cause is a surge in carbon-based molecules, specifically C2 and CN radicals, released as the comet's carbon dioxide content vaporized under intense solar heat. This green luminescence is more than a mere visual anomaly. It is a chemical fingerprint revealing that carbon dioxide, rather than water, is the dominant component driving the outgassing. This fact alone distinguishes 3I Atlas from the majority of known comets, whose activity is typically fueled by water ice. The chemical profile continues to reveal further strangeness. Spectra obtained from both hemispheres, along with embargoed preprints circulating among specialist teams, point towards a nickel-to-iron ratio far exceeding the typical bounds observed within the solar system. Nickel emission lines, prominent and persistent, overshadow their iron counterparts by margins that suggest an origin within a supernova remnant or the stripped core of an ancient, differentiated planet. If confirmed, this discovery would necessitate a revision of our fundamental assumptions about the types of debris capable of surviving interstellar journeys. The dust itself, as illuminated by polarimetric studies, displays extreme negative polarization. The light scattering pattern indicates a predominance of fine, possibly glassy or metallic grains, rather than the silicate material familiar from comets within our local environment. Morphology presents yet another puzzle. Instead of a classic anti-solar tail, 3I Atlas exhibits a coma that is brightest on the sunward side, with a forward scattering envelope that defies conventional models of dust and gas expulsion. The sun-facing edge gleams with a density and texture that has incited heated debate among observers. Some posit a jetting phenomenon, while others suggest a sheath of highly reflective, metal-rich dust. The anti-solar tail, if it exists, remains faint and elusive, a mere whisper against the solar glare. The light curve, meticulously tracked in the weeks preceding solar conjunction, adds urgency to the mystery. Rather than diminishing as anticipated, the comet's brightness steadily increased even as it crossed the orbit of Mars and entered the sun's immediate vicinity. This pre-gap brightening, recorded in the final days before the data blackout, ignited a storm of speculation across all observer channels. Could it be an indicator of fragmentation, a renewed outburst of volatile gases, or simply the revelation of fresh surface layers never before exposed to sunlight? Each anomaly, size, color, chemistry, polarization, coma characteristics, and geometry, has captured the attention of a vast, loosely coordinated community of observers. Professional astronomers, amateur stargazers, planetary scientists, and instrument specialists have converged in digital forums, racing to decipher the object's secrets before technical limitations and the sun's glare impose silence. Their findings, their arguments, and their unanswered questions now set the stage for a more profound confrontation with the limitations of our instruments and the boundaries of current cometary science. Magnitude 12, that is the predicted brightness of 3I Atlas as it sweeps behind the sun, fainter than any planet and far below the detection threshold of most solar observatories. For instrument engineers and data analysts, this single number defines the practical boundary between optimistic hope and tangible measurement. Coronagraphs, such as SOHO's LASCO C3 or Stereo's heliospheric imager, are designed to mitigate the sun's glare and reveal significant outbursts, but their detectors are calibrated for objects at least 100 times brighter than this interstellar visitor. Even with extraordinary digital processing, the surface brightness of the coma falls short. The comet's angular size, a mere few arcseconds at best, renders it indistinguishable from the background noise of the solar corona. No confirmed detections have emerged from any sun-focused spacecraft, not from SOHO, not from Stereo, not from Parker Solar Probe, and not from Solar Orbiter. The standard data products, those daily visual records of the inner solar system, display nothing but turbulent plasma and the occasional planetary body. For 3I Atlas, the signal-to-noise ratio stubbornly remains below 1, even when hundreds of images are meticulously stacked. The coma's faint, diffuse glow is simply overwhelmed by the ever-shifting light patterns that surround the sun. Some teams are proposing a workaround, shift and stack. The concept is elegant in theory. Hundreds of images are captured, the comet's apparent motion across the detector is predicted, and each frame is digitally aligned so that any faint moving object is amplified, while static background features are cancelled out. In principle, this method can enhance the detection limit by a full magnitude or two. In practice, however, it demands an accurate ephemeris, precise knowledge of the comet's trajectory, and a willingness to sift through terabytes of noisy data in pursuit of a single, faint smudge. For 3I Atlas, even the most optimistic shift and stack campaigns, involving 100 frames from LASCO and 50 from Stereo, still fall short of a secure detection. The mathematical calculations are unforgiving. The anticipated gain in signal-to-noise ratio is overwhelmed by the sheer faintness and compactness of the coma. Instrument safety protocols introduce an additional impediment. As the comet's solar elongation drops below critical angles, automatic shutdowns are initiated to safeguard sensitive detectors from accidental exposure to the sun's disk. No amount of manual override can justify risking a billion-dollar imager for a target that may not even be visible. For ground-based telescopes, the situation is even more challenging. The sun's glare saturates the sky, and no amount of adaptive optics or horizon-hugging observation can extract the comet from the atmospheric haze. Mars orbiters offered a brief glimmer of hope. Their unique vantage point allowed for a handful of long exposure images in early October, but by the time perihelion was reached, their orbital geometry and instrument limitations had closed that observational window. No high-end telescope on Earth, in orbit, or circling Mars remained in position to witness the critical moment of peak solar heating. For the present, the data gap is absolute. The world's most advanced coronagraphs and heliophysics imagers are compelled to acknowledge defeat. 3I Atlas is simply too dim, too small, and too close to the sun for any direct measurement during its conjunction. The only path forward lies in creative data mining, reprocessing existing exposures, stacking images along predicted paths, and holding out hope for a post-conjunction surprise. Instrument teams are already formulating contingency plans for future interstellar visitors, including more flexible safing protocols, dedicated shift and stack processing pipelines, and perhaps, one day, solar observatories specifically designed to track faint comets through intense glare. For now, the boundaries are clear. The object is out there, traversing unseen, and the instruments built to detect it have met their match. At the precise moment 3I Atlas swings closest to the sun, a new set of profound questions comes into sharp focus. These are questions that extend beyond conventional cometary models. Among the most vocal proponents are advocates of electromagnetic explanations, often referred to as electric universe theorists, who contend that comets are not merely frozen relics, but active participants within the solar plasma environment. For them, perihelion represents more than a gravitational checkpoint. It is a natural laboratory where the solar wind, electric fields, and charged dust particles could interact in ways that leave measurable signatures. One hypothesis currently under consideration suggests a sudden surge in activity triggered not solely by heat, but by the object's passage through regions of intense electromagnetic flux. If the comet's carbon dioxide-rich dust is electrically charged, the sun's magnetic field could accelerate these particles, alter the coma's morphology, or even cause a detectable shift in its trajectory. These effects would manifest as subtle yet real deviations in post-perihelion tracking data. Specialists in dusty plasma physics are already developing diagnostic metrics. These include detecting changes in coma polarization, observing unexpected drifts in the outbound path, or registering a burst of radio emission as the solar wind impacts the dense, metal-rich envelope. No one is asserting certainty. These are testable predictions, not definitive pronouncements. When 3I Atlas reappears in November, every new data point, its brightness, position, and coma structure, will serve as a diagnostic tool for mission planners and alternative theorists alike. The subsequent phase is a waiting game, with the hope that nature itself might provide a verdict on theories long relegated to the fringe. Astrologers observing the celestial sphere during perihelion note a rare alignment of cosmic bodies. As 3I Atlas navigates the constellation Virgo, it stands in direct opposition to Chiron, with Eris in close proximity, while Jupiter and Pluto form their own distinct axis across the heavens. Chart interpreters interpret these alignments as a grand cross, overlaid with kite and grand trine configurations, motifs long associated with periods of crisis, profound transformation, and the pursuit of deeper meaning. Some interpret the comet's passage through Virgo as a symbolic representation of healing through disruption, a reminder that even the most alien visitor can catalyze ancient patterns of introspection and renewal. For those who follow planetary cycles, the timing resonates deeply. 3I Atlas makes its closest passage by Earth just before the winter solstice, a season marked by the transition from darkness towards light. Its outbound journey brings the traveler into close proximity with Jupiter by March, a progression that, within astrological tradition, hints at the potential for new beginnings and shifting collective priorities. Whether these patterns are perceived as cosmic metaphor or mere coincidence, they offer a bridge connecting scientific observation with the human endeavor of meaning-making. For individuals interested in commemorating this celestial event, a special commemorative design is available. The narrative of 3I Atlas continues, woven from both empirical data and imaginative speculation. As the world awaits its reappearance in our skies, key questions persist. What is the underlying driver of its anomalous behavior? Will perihelion induce significant changes in its activity or trajectory? These answers await its reappearance in mid to late November. As the data gap persists, each new observation of 3I Atlas will serve to test our comprehension of interstellar visitors and the current limitations of solar system science. For now, only the archival record remains, a testament to how much still lies hidden, even as the evidence continues to accumulate.